Hello, welcome to the aromatic chemistry topic. So then, we're going to start off with some questions which are pretty much just year 12 content, alkanes and alkenes. So pause the video and have a go at these questions. Okay, so you should already have produced a set of answers to these questions, or at least the ones of them that you could have a go at. So here we go. Here are your solutions. Cyclohexane looks something like that. Doesn't matter about the exact geometry or orientation of it at this level, but it should look something like that. I gave several examples of isomers for 3, 4 and 5. There are obviously different ways you can go with this, but I just tried to pick the most obvious answer. So functional group isomer of cyclohexane, hex 1-ene, you could obviously have hex 2-ene or hex 3-ene. And that kind of goes on into the, into the chain isomers and the chain isomer of the functional group isomer. The bonding question, the answer has to be cyclohexane because it has a higher boiling point due to being a larger molecule with more electrons or a larger surface area or whatever, so stronger van der Waals forces which require more energy to overcome. So then, those questions are all about cyclic compounds, and that links quite strongly to what we're about to do, although we're not looking at cyclic alkanes. So then, here are the facts. Aromatic chemistry is all about a compound called benzene and its derivatives. Okay, so benzene is a cyclic hydrocarbon and it has the molecular formula given in the slide. Your job is to pause the video, try and suggest a structure for benzene, and then give the empirical formula that relates to that molecular formula. So you're looking at this and you're probably going to come up with something that looks a bit like this initially. So we know that it's got 6 carbons joined in a ring. And it's got 6 hydrogens, and the logical thing to do is to put 1 hydrogen on each carbon, right? Then you may have also come to the conclusion that that means there must be some unsaturation. And so you may have drawn something with alternating double and single bonds like this. The reason that this structure is important to arrive at is it satisfies the kind of condition that carbon needs to form 4 bonds. If you look at each carbon atom, it will have formed 4 bonds. And the empirical formula looks a little strange in this one, but it's perfectly kind of logical. You divide down C6H6 and you get CH. This is an important structure which we're going to look at in quite a lot of detail as we go along. All right, and it is a given structure for benzene, but you'll see what I mean soon. So then, the way that we normally draw a benzene ring at A level is it actually looks like this. So the molecule that we just drew is more appropriately drawn like this, like a hexagon with an unbroken circle in the middle. So this is called a benzene ring, and that's supposed to represent a cyclic hydrocarbon with a molecular formula C6H6. There are a couple of maybe new words here. The benzene ring often has substituents. I'll explain what that means in a minute. And this class of compounds, as well as being called aromatics, sometimes called arenes, a bit like alkenes, except aromatic. So, let's talk a little bit about the word substituent. We can go back to this diagram to help with that a little bit. What we mean by that is, quite frequently, a hydrogen atom on the outside of the benzene ring might be replaced with some other atom or some other functional group. So, there's chlorobenzene. That thing has a couple of names. It's probably called phenol or hydroxybenzene. So that's what we mean by substituents. So just a little bit on naming, right? When you name derivatives of benzene, you can either put the benzene at the end. So for example, methylbenzene. That is a benzene ring with a methyl group on it. If you were keeping it skeletal, you'd keep it like that, or sometimes it might be drawn like that. Chlorobenzene, we've already kind of looked at that, but just to make it perfectly clear, that's when you've got a chlorine attached. Sometimes, due to how the name works, you put the word phenyl at the beginning. So the idea is that when the benzene ring is kind of considered as being attached to something else, where it's not the main part of the molecule, if you like, you call it a phenyl group. Okay, you might well have seen that before because there's an amino acid with a phenyl group in it, phenylalanine. So in this example, phenylamine, we're basically considering the benzene ring to kind of be the extra part of the molecule, and then the NH2 group is the part that represents amine. Now, naming aromatics can be quite complicated. In fact, it's, if you're a organic chemistry student at A level, it's a bit like a wild west of naming because it seems like the rules just get bent, in a crazy way. The main thing is to not worry about it too much. If you can name a couple of simple benzene derivatives, then you're doing okay. There tends to be a little more flexibility and a little less little less of a system in how we name aromatics. Okay, so it's just a little word on it, and we will do a little bit of it as part of these lessons, but it's not a big deal basically. So then, something that is a big deal. There are two sort of representations of benzene you need to be aware of. The first one is a skeletal version of what we arrived at in that question where I drew it in yellow, where I asked you to do it on a whiteboard. The next one is kind of called the modern structure, or the A-level structure of benzene, I suppose you could call it. So there are two ways of representing benzene, and we have to look at the differences between the two and why one of them is better than the other. Right, that's a big part of the benzene sort of topic, or the aromatics topic, I should say. So, right, let's have a little look at this thing, the Kekulé structure. So this is the same thing that we arrived at earlier on. Geometry, I might have moved the double bonds around, but it's the same molecule, okay, alternating double and single bonds. And it definitely satisfies the criteria for having the molecular formula C6H6. But it's kind of a historical structure, and it's called the Kekulé structure. What I now want you to do is to try and pause the video and see if you can name this molecule. So the name you should have arrived at should be something like cyclohexa 1,3,5 triene. So just to be clear about that, 6 carbon atoms in a cyclic arrangement, and we're saying that this is carbon 1, we're actually going in this direction, that's carbon 3, and that's carbon 5, and that makes that carbon 6. So we're naming the double bonds for the lowest number of the carbon that they're attached to, 1, 3, and 5. So the important thing to point out about this, and we might as well be upfront about it, this is a theoretical molecule which does not exist, right? What we mean by that is the Kekulé structure is wrong, okay? There is no molecule with actual alternating single and double bonds and 6 carbons in a ring, right? Instead, the benzene molecule that we know has a structure that's more akin to the kind of picture that was on the right earlier. Having said that, you still see the Kekulé structure everywhere. Loads of people still use it. Even though it's wrong, it still gets used, and that's just one of those things that you kind of have to contend with. If you Google any kind of aromatic compounds, chances are you will see an image of Kekulé structures of benzene in that molecule rather than the one with the circle, okay? But it is not correct, it's a theoretical molecule, okay? There's a nice little scientific story behind this. You can look into it yourselves, but it's named for a scientist called Kekulé, and the story goes that for one reason or another he was dreaming about snakes eating their own tail, and that's how he arrived at this kind of cyclic molecule arrangement. That's not really an important part of the A-level, but it's interesting for flavour and for context. So, here's an important kind of piece of information. In the modern structure, we know that you don't have alternating, discrete, separate single and double bonds. Instead, you have this kind of ring of delocalized electrons. Okay? So there is kind of a halo, that's the best way of describing it, a halo of delocalization, but it's actually above and below the ring. And this gets very, very complicated. It's to do with how electrons kind of position themselves, or, probability of places you might find an electron. And it goes beyond A level. But benzene, if you view it from the side, is actually a planar molecule. So let's take the structure here, and if you rotate it slightly, what we're basically saying is you will see electron density above, that's what the first blue ring represents, and below, that's what the second one represents. If you take that structure and you turn it, completely sort of 90 degrees, right, you will just see this, right? As if you could just view it, but the idea is that you would have electron density above and below the ring. And that's represented just by this circle, right? You don't ever draw it the way that I have done down here. That's just to try and explain that the electrons are above and below. If you're sort of interested in this and you want to know more, you can read a little bit about pi bonds in alkenes. That will help you understand a little bit, but I'm not going to go into it any further because you don't need it for A-level. So, it's all very well and good me telling you that Kekulé is wrong and the modern structure is right. There are 4 pieces of evidence that we use for this. 3 that are the most important, so I'm just going to highlight those. The first 3 are the ones you're usually asked about. The 4th one is kind of an extra one, really. So you need to pause the video and make your notes here, right? And I'm going to tie up this video, which might seem short, but it's just an introduction. And in the next video, what we're going to do is we're going to sort of unpack each of those pieces of evidence in detail.